Good morning, welcome to a new lecture. Today I will review again several examples. The first example, it is simply supported beam. Subjected to concentrated load at mid-span. But the half of beam is rigid, means EI from A, B, C, if I name it ABC, point load, it is at point B. From here to here, it is L over 2, L over 2. But EI for AB part, it goes to infinity. Means the cross-sectional area is very big. EI for BC part, it is constant. We want to find deflection at point B. So using virtual work method, first I will draw moment diagram under real load. For simply supported beam, moment will be positive and this will be PL over 4. Why? Because the reactions, this is P over 2, P over 2, it is symmetrical system. You don't need to use equilibrium equation, it is common sense. If I apply P, contribution of each support will be half P over 2, P over 2. Moment at mid-span, if I move from A to B side, and just before B, what is the moment? Moment will be P over 2 times distance, L over 2, it will be PL over 4. Why it is positive? Because beam deforms downward and underneath of the beam we have tension. Tension underneath of the beam means positive moment. Now, because I want to find deflection at point B, I should create my virtual system. For virtual system, I will add unit load at point B again. Moment diagram will be similar. Instead of P, you will plug 1 because you had P, now you have 1. So it will be L over 4. Now, if I want to find delta B for this side from A, B, C, A, B, C. If I multiply, for AB part will be triangle to triangle. The coefficient is 1 over 3 times PL over 4 times L over 4 times length for that part, which is L over 2, divided by EI. EI for that part, it is infinity. So these terms will be 0 plus triangle to triangle 1 over 3 PL over 4 times L over 4 times L over 2 divided by EI. The answer will be PL3 over 96 EI. If both sides can deform, if you remember for simply supported beam, if EI for entire beam, is constant, if you remember deflection was P L cube over 48 EI. If half of beam, AB part, it is rigid, means that part will not deform. The deflection for point B will decrease to half. It will be PL cube over 96 EI. For example, if the answer for this is 1 inch, this will be half inch. And it makes sense. Let's look at the next example. Assume we have one frame like this. From here to here is 3 meters. 3 meters. The height is 4 meters. Here A, B, C. At joint B, which is rigid joint, we have concentrated moment of 1 kilonewton meter. EI for entire frame is constant. I want to find theta B. What I will do, first I will draw moment diagram under real load, then I will apply unit moment because I want to find rotational stop at point B. I should apply unit moment at point B. Then I will multiply those diagrams together. First step, if I assume dashed line inside of this frame, the moment diagram under real load, if I find this reaction, finding this reaction Cy is very easy. How I can find it? If I take moment respect to A, Cy times 6 minus 1 is equal to 0. So Cy will be 1 over 6 kilonewton. If I write summation of forces in vertical direction is equal to 0, Ay plus Cy is equal to 0, we will figure out Ay, it will be negative 1 over 6 or 1 over 6 downward. Now, after finding these reactions, I should draw moment diagram. Moment at point C, it is equal to 0 because it is hinge. Hinge means inside of the hinge, internal moment at hinge always is equal to 0 because hinge is a system, cannot resist against moment. So point C moment is equal to 0. At point B, what is the moment? If I cut here, the moment will be load times distance. Cy times distance 3. So 1 over 6 times distance 3. Pay attention, you will not multiply to this length because always load times distance, which is perpendicular to the load, will create moment. So from here 1 over 6 times 3 will be half. Moment at point B will be 0.5. Negative or positive moment times distance at point B. Our moment, it is in this direction. So bending like this, that moment will create tension. Or if we look at the deformation of this frame will deform like what? Because we apply external moment clockwise, point B will rotate clockwise. So something like this will be deformation. This region, you see this region, we have tension, so positive moment. AB part will be negative moment. So everything is the same, but here will be negative 0.5 and again 0 because point A, again it is hinge, moment is 0. If I move from A to B side just before B, if I cut it, 1 over 6 times 3, it will be half. Negative or positive, that moment create compression in dashed line, so it is negative moment. This will be moment diagram for real load. Under virtual load we want, because find it, stop at point B. This time I will have the same structure. I will apply unit moment at point B. External load, it is unit. So virtual system, again we will apply unit moment. So the moment diagram will be identical. Moment diagram again will be the same. Everything is the same. So if I want to find theta B now, what I have, this triangle to this triangle, this triangle to this triangle. Everything is the same. The length of the triangle, the moment diagram. Here negative to negative is positive, positive to positive it is positive. So I can calculate to one side multiplied by 2. It will be 2 times maximum moment under real load, maximum moment under virtual load, times the length of element. If from here to here it is 3, and from here to here it is 4 meters. Let's look at here. This is 3, this is 4. So the length for AB we can find it is 5 times the length of AB part, it is 5 times EI times triangle to triangle coefficient is 1/3. That will be 0.83 EI. That will be rotation at joint B. Next example. In this example, we have one frame, 2 elements with rigid joint like this. This is rigid joint. A, B, C. The length for AB is L, the length for BC is L. EI is constant again. We apply load P at point C and the load P at point A. We will apply this load, so it is clear the distance between A and C will increase. This will deform like this. Point B will transfer down. This is bending like this. This is bending like this. And so point A will transfer to point A prime. Point C will transfer to point C prime. So the distance from A to C will increase. We want to measure to see how much the distance between A to C will increase. So we have this system. The length for AB part is L, for BC part is L. EI for entire system it is constant. We apply one load here, P another load here, and we want to measure how much the distance between point A and C will increase. The angle between P and BC it is alpha. This angle is alpha as well. So again what I will do, first I will draw moment diagram for real system. Moment diagram for real system. If I put dashed line in interior of this frame, and if I apply load and load, deformation will cause tension. So both moments should be positive. Point C it is 0, point B will be P times distance. If I move from C to B, if I cut here, what is the moment? Moment will be P times the distance which is perpendicular to the P, this distance. If this is L, this distance will be L sine alpha. So moment diagram will be 0. It goes to positive PL sine alpha. Moment at the beginning at free end is 0. Just before B it is load times distance which is perpendicular to the load direction. That distance from B to C it is L. This angle is alpha. So in vertical direction distance will be L sine alpha. P times L sine alpha will be our moment. Because this is rigid joint, we will have the same thing here. Symmetrical system. Our moment diagram should be symmetrical too. So PL sine alpha. Next, because we want to measure the distance between A and C and to see how much it will increase, it will deform from both sides. It will deform from A side, it will deform from C side. So we should apply unit load at point A, unit load at point C. Again, everything will be the same. Just instead of P, you will plug 1. So moment diagram this time will be positive L sine alpha, positive L sine alpha. Now we will multiply this triangle together, and because it is symmetrical, we will multiply this to this one, multiply by 2. So delta AC means how much the distance will increase between A and C is equal to 2 times triangle to triangle, the coefficient is 1 over 3, times moment in real system PL sine alpha, moment in virtual system L sine alpha, times the length of the element, it is L, divided by EI. The answer will be equal to 2PL cube sine square alpha over 3EI. Let's look at the next example. We have this frame. We have load 2P here. The length is L. The length is L. For this BD part it is 2L. EI, EI, and 2EI. So for each beam AB and BC, the length is L and EI is constant. For column BD, the length is 2L and the EI is 2EI. We apply load at point C. We want to find rotation at point B and rotation or slope after deformation at point D. Slope at point B, slope at point D it is clear this system will deform like this. Let's see. Something like this roughly. It will deform like this, so point B and point D will rotate. We want to find slope at point B, slope at point D. First step, I will draw moment diagram in real system. Moment diagram here. Moment at point C, it is free and it is 0. If I put dashed line underneath of this beam, moment P for B, if I cut it here, moment will be 2P times L, and it will create compression underneath. It is negative 2PL. Moment at point A is 0 because it is hinged. There is no force at AB part, so from 2PL will come to the 0. Moment diagram, and in this element, BD element, or in that column, will be 0. Why? Because if I find dx for action, summation of forces in horizontal direction is equal to 0, this is 0. If I take moment respect to A, I will have dy times L minus 2p times 2L is equal to 0. From there I can find dy will be 4p. If I write summation of forces in vertical direction, Ay plus 4p minus 2p is equal to 0, so this will be 2p downward. For BD element, for that column, there is no force perpendicular to that element, so the moment diagram will be 0. Now let's draw moment diagram under virtual system, under virtual load. I want to find slope at point B. First, I will apply unit moment at point B. So here the moment will be 1. At the end it is 0. If I find reaction again, you can double check. This will be 1 over L. This will be 1 over L downward. So for theta B, I will apply unit moment at point B. In that case, moment diagram for BC part, it is 0 because C is free. No load at BC part, it is 0. For BD part, it is moment diagram, it will be 0 because again there is no force perpendicular to the BD, because dx will be equal to 0 again. But because I am applying unit moment at point B, so here the moment is 1 and that support traction will be 1 over L downward, 1 over L upward. You can find this. So these two systems, if I multiply together, theta B will be equal to 1 times L times 2PL divided by 3EI, because triangle to triangle, the coefficient is 1 over 3. 1 times 2PL, negative times negative is positive. Coefficient 1 over 3 times length over EI. So the answer for this system will be equal to 2PL square over 3EI. Moment times the length divided by EI times 1 over 3 coefficient. In order to find slope at point D, this time I will apply the unit moment at point D1. So in that case, again, this will be 1 over L. This will be 1 over L. Moment diagram this time, if I put dashed line in left side of the BC, it will be under compression, negative 1 Here will be again 1. This will be 0. Because the BC part, it is free part, there is no force perpendicular to the BC, no moment, this is 0. So again I will multiply these together. Rectangular times 0, it is 0. Again triangle to triangle, it will be the same thing. Theta D will be equal to 1 times L times 2PL divided by 3EI. That will be equal to 2PL squared over 3EI. I think for today is enough. Review these examples. During again other sessions, I will solve more problems. Thank you so much for watching this lecture. See you next session. Bye bye.